Thank you very much, everyone. Welcome to our winter term seminar series on blockchain. This is our second year with this seminar series. We've lined up a number of speakers, starting with our very own colleague, Peter McBurney from the Department of Informatics. And then we'll have other speakers from Oxford and Columbia. Peter's topic today is distributed ledgers as the second great revolution in IT, how shared data platforms are transforming business. And Peter is professor of computer science in the Department of Informatics, and he was head of department between 2013 and 2017. His first degree is in pure mathematics and mathematical statistics from the Australian National University in Canberra, and he has a PhD in artificial intelligence from the University of Liverpool. His research focus has been on the design of artificial languages and protocols for automated machine-to-machine communications, agent-based simulation modeling, particularly in finance and economics, and more recently in distributed ledgers and blockchain systems. Peter was a PI on several networking projects and other big, large research projects funded by the European Commission. And he's currently actually co-editor-in-chief of the Knowledge Engineering Review, a refereed AI journal published by Cambridge University Press. This being said, Peter, thank you very much for having accepted our invitation, and over to you.
Thank you, Alex, and good afternoon or good morning, depending on where you are in the world. Good morning and good afternoon, everyone. As Alex said, I'm here to talk to you about distributed ledgers. Thank you for the honor and the privilege of giving this talk. As many of you know, the technology of distributed ledgers and blockchain began with the cryptocurrency Bitcoin. And so my talk will talk a little bit at the beginning about Bitcoin. However, the main thrust of the talk is about distributed ledgers and about the technology that underlies Bitcoin, not about cryptocurrencies. And I'm giving the talk, or my emphasis is about commercial application of these technologies. I think there's a great deal of misunderstanding and indeed some fake news, some deliberate false information that has been put about the applicability of these technologies and their worthiness in commercial applications. And so I hope to counter some of that in the course of the talk today. Feel free to ask me questions as I go through. Because this is a multidisciplinary seminar series, then I hope to have a bit for lots of different disciplines. And some of it might be stuff you've already seen. I know some of you in the audience know a great deal about parts of this subject. So please excuse me that it might appear shallow, but that's because I'm trying to be broad in what I cover. The subject is indeed broad and the implications are extremely broad. So I'm going to move through the slides. I hope you can see the slides. Yes. So I first start with two quotations, one from the British government's former chief scientific advisor, Sir Mark Walport, who wrote in a report a few years ago, "We may be witnessing one of those potential explosions of creative potential that catalyze exceptional levels of innovation." And that was talking about in a report about blockchain technology. The other quotation comes from a vice president, also retired of Barclays Bank, named Jeremy Wilson. And his statement to me was that he wished he was 30 years younger because this is really interesting stuff. And he's right. It's definitely a technology, a revolutionary technology, as I'll explain going through. So the origins of blockchain and distributed ledgers lie in Bitcoin. Bitcoin was the first working example of a blockchain distributed ledger system. I'll explain a little bit about the terminology later in the talk, but at the moment we just treat them as interchangeable, blockchain and distributed ledgers. In practical use, they mostly are interchangeable, although there are some subtleties. The problem that Bitcoin tried to solve was to have a system of electronic money that ensured that the money was, the electronic money was authentic, that it wasn't counterfeit or could not be counterfeited. In particular, that the same parts of it, the same pieces of electronic money, could not be spent more than once. That's called the double spend problem. And you can solve that problem very easily if you have a trusted person at the center. If you have somebody who is in charge of the database of who has which money at any one time, and that person or organization is trusted and they can be guaranteed to be reliable. This is a challenge for any enterprise or collective activity by a group of people that may have some illegality associated with it, some criminal activity. How can you set up a criminal enterprise with a trusted person at the center? And the best example of this that I know of is Silk Road, which was a marketplace for illegal drugs initially, and then subsequently a marketplace for other illegal enterprises, even perhaps murder for hire. The person or persons who set it up seemed to be trustworthy at the beginning. The ones that the person who's been arrested and put in prison for the rest of his life, Ross Ulbricht, seemed to engage in distrustful behavior, untrustful behavior later in the period in which he's alleged to have been running it. The problem that the developers of Bitcoin blockchain wanted to solve was how to do this, how to have electronic money without such a trusted person in the center. So can we devise a computational system which allows us to do away with the trusted center, to make it truly decentralized and not rely on the trust of an individual or an organization? And Bitcoin solved this problem. It was the first truly decentralized system for electronic money. Interestingly, the innovation in Bitcoin was not any particular technology. It used previous technologies, but it put them together in a very clever way, in a very thoughtful and what proved to be a very useful way. So the previous technologies that Bitcoin drew on was asymmetric key cryptography, which is a system of a public and a private key, sometimes called public key infrastructure, PKI. It used Hashcash, which was a proof of work system to make spam too expensive to undertake back in the early 90s. It built on ideas that had applied Hashcash to electronic money, such as a project called B-Money, wherein the system, all the transactions of the system were witnessed by all the participants. And it used protocols from the branch of computer science called distributed systems. In that branch of computer science, we refer to consensus protocols. And I think that terminology, which is very specific and very technical, has misled a lot of people who come to this from outside computer science. It's not, the consensus is a consensus of machines. The machines are not generally deliberating in any way that a philosopher or a political scientist would understand deliberation or understand the word consensus. So beware, the terminology of consensus protocol, as with other terminology in this domain, comes from computer science. There's an underlying philosophy that was evident in the Bitcoin blockchain from the cypherpunk movement. So these were people who were advocates, these still are indeed, people who were advocates of cryptography and privacy technologies for social and political change. And they saw, and they still do, see e-money, electronic money, as a way to avoid government control. And this is still a large section of the cryptography community. Who was the founder? Well, he, she, or they went by the name of Satoshi Nakamoto. I've put some photos on the slide there of possible candidates. The man on the left is a Japanese American who worked in security, whose name is indeed Satoshi Nakamoto, but I don't think it was him. The press thought it was him for a while, but I don't think so. The man in the top middle is the Phantom, famous cartoon character, may have been the Phantom. The man in the top right is Ross Ulbricht, who is the person I just spoke about as one of the, maybe the founder, I'm not sure, but certainly one of the instigators and managers of Silk Road, the drugs marketplace. The man in the middle, below the Phantom, is Hal Finney, who may or may not have been Satoshi, or may or may not have been part of Satoshi, but was certainly one of the very early users. So maybe user number 2 or number 3. So he was associated with the people behind. He's unfortunately dead, so he can't tell us anymore. And the man in the bottom right is my fellow Australian, Craig Wright, who claims he is Satoshi Nakamoto. So far, he has failed every test of that claim, but he continues to claim. The article I quote down there by Andrew O'Hagan is a very interesting, a long and very interesting article based on extended periods spent with Craig Wright talking about this question. So at the moment, we don't know. My belief is that it was a team, and I have that belief because the different technologies used come from very different parts of computer science. And it's most unlikely one person would have known about all those technologies in advance. And if they had known about all those technologies, they would have developed it earlier. So the fact that it only came along then says to me that when it did, it says to me that it's a team, maybe a private team, maybe a team in a government, we don't know. What does it involve? Well, the blockchain for Bitcoin, it was intended, it was created and designed specifically for the cryptocurrency Bitcoin. Subsequently, we've seen many applications of blockchain technology that are not intended for cryptocurrency. And so there are differences different things you can do, different design elements you can alter for these different applications. Satoshi Nakamoto published a white paper. You can still find that on the web, published that at the end of 2008, I think November. And then early January, he released the code and created the Genesis block, the first block. The properties of this blockchain that is specific for Bitcoin, there's no central authority. It's decentralized. By very clever techniques, it prevents almost completely, not entirely, but almost completely prevents double spending of currency. It's open and public. And people commonly say that it's anonymous. It's strictly speaking pseudonymous, because to participate in it, you have an address, and that address may provide information about you outside the system. So if I transfer money, transfer Bitcoin to someone on a regular basis, that would indicate I've got some sort of relationship with them outside the system. So that was why we say it's not strictly anonymous. And the whole thing is enabled by blockchain. What happens with this blockchain technology for Bitcoin? Well, transactions represent exchanges of Bitcoin, exchanges of the currency. Those transactions are signed by digital signatures. They use this public key infrastructure. Transactions that are accepted are aggregated into blocks and uploaded, and blocks of transactions are chained together. So that's where the name blockchain comes from. We're putting transactions together into clumps, and we're chaining those clumps together, those blocks together. The process of aggregation and chaining is done by nodes that are called miners. And doing this takes some processing power, some work, and the miners are paid in Bitcoin. The next bullet is a technical bullet about computer science, but basically the headers have dynamic membership multi-party signatures based on the power that the nodes have to do the work. So it's based on some measure of computation power. It's not based on knowledge or permission or any other variable. And then we use cryptographic hashing, putting things into encrypted form to chain blocks together. And I'll talk about this in a moment. So what's a good way to think about this? I found a couple of metaphors useful talking to people who are not computer science. So the first metaphor is about coffee transactions. We might have, for some reason I won't go into, but we might have, a group of us might decide we want to keep track of our coffee consumption. And so what we're going to do is every time we buy a coffee, we're going to get a receipt of that transaction, and we're going to share all our receipts together, and we're going to bundle them in a particular way I'm going to describe. So what we're going to do is the first receipt, say I collect the first one, so I take the receipt, I make multiple copies of that receipt. Say there's 5 of us in the group, then I make 5 copies. I put each copy in an envelope, and I put on the outside that this is receipt number 1 on the envelope. And I give those 5 envelopes to my 5 friends. So sorry, 5 of us in the group, so 4 friends. I keep one for myself and give 4 copies to my 4 friends. One of them is the second person to buy a coffee. So they do exactly the same. They take that receipt, they photocopy it, but they make 4 copies of it. They put those 4 copies in an envelope, and on the outside they write envelope receipt number 2. But also in the first envelope, sorry, in the second envelope, they put their copy of the first envelope. So you've got a nesting of envelopes, and in each envelope is also a receipt, most recent receipt. And we do this receipt after receipt after receipt. Now, this would quickly get to be cumbersome if we were doing it in the physical world. It would quickly get, the envelopes would quickly get to be too big. You wouldn't be able to hold everything in the envelope. But this is the idea of putting transactions into blocks and bundling the blocks and linking them all together. So we're putting envelopes inside envelopes, inside envelopes, inside envelopes. And everyone has a copy of the complete set from the beginning all the way through up to the most recent one at all times. So what the system does is a very strange and ironic, what the blockchain system does, a very ironic system. It provides a form of trust in the transactions by having everything done in public and being witnessed and everyone having a copy. So if I wanted to alter one of those receipts, if I decided that for reasons of defrauding my taxes or something, I wanted to change the date of my receipt, I would have to change it in all the copies. I would have to get the most recent envelope and open the envelope inside that and open the envelope inside that and open the envelope inside that, all the way back to the first envelope and then make a correction. And I'd need to do it not only to the copies of the envelopes that I hold, but I would need to do it with my 4 friends on their copies as well. And this could not be done without them seeing me do it. And in the Bitcoin system, they would have to approve me doing it as well as seeing me do it. So the system of copies being sent to everybody, or copies being approved by everybody, and everybody having a stack of those from the very beginning means it's very open and transparent. But that's what creates the trust. So to me, it's an ironical situation that we get trust from the openness and the witnessing. So as we just said, this is a system where there's no central authority. There's no need to trust anyone else. The witnessing is done by the entire community on the blockchain. Chaining makes it very difficult, not impossible, but very difficult to alter past records, because we need to alter all the records since the one we want to alter, all the subsequent records as well. Witnessing makes it hard to alter or to create false past records. And we have to get everyone, at least everyone who has mining power, to give us a majority of the mining power, to agree to a new chain. And really we can, if we want to alter the past, the only effective way to do it is to fork the system, which has happened with some of the commercial systems. This has happened with the Bitcoin system as well. So the double spending is prevented by the consensus protocol, the consensus protocol and the community witnessing of the system. The protocol used in the Bitcoin blockchain is something called proof of work, and it's part of the protocol for validation and consent. So why is it necessary? So Bitcoin is open, and the designers of it, all of us who use it, need to motivate the process of validation and processing. This takes a little bit of computational effort, not a great amount. It takes a little bit, and the nodes need to be motivated. So the way that Bitcoin motivates them is to give them a reward in the form of Bitcoin. So they get new Bitcoin if they are successful in uploading a block. They also get fees from the transactions that are inside the block. So there's another reward to the node that uploads. But this is an open system. So we don't know anything about who the nodes are, except we know their address. And it's possible that a node could join multiple times. It's less likely now because there's 11,000 something nodes. So, but in the early days when there were less than 100 nodes, a node could easily join 40, 50 times and take over the network. So how do we know that isn't happening? That isn't happening? How do we know it hasn't happened? Well, one way to do this very clever technique of the Mr., Mrs. or they, Satoshi, was to say, we won't only give nodes rewards for uploading blocks, we'll make them do some work as well. So there's a cost to uploading. And the fine art of the design of the blockchain is to ensure always that the reward is slightly more than the cost. It's no point the reward being less than the cost because no one will do it. If the difference is too great, then that will enrich nodes perhaps too much. It will motivate them too strongly. So what the designers did, what Satoshi Nakamoto did, was to say, well, we're going to ask you to do some work, and what we're going to do is ask you to solve a computational problem. This is called proof of, and provide proof that you've solved it. This is called proof of work. It's not the only protocol. It's not even the best protocol necessarily. There are a lot of protocols around. Proof of stake, which Ethereum has started transition to, proof of authority, which is what most of the permission systems that I'll talk about today use. Proof of identity, which is a related, proof of elapsed time, which is a system Intel invented that's sort of a proof of authority. There are different, very different protocols, and they, part of the challenge or part of the excitement of this technology at the moment is that we are still finding the pros and cons of those different protocols. So who are the users of Bitcoin? Well, many of these you will have heard of because there's so much talk about them. It's clear from the documents, the white paper and other documents at the time, that Bitcoin was founded, that online gambling was probably a main application of Bitcoin. People who are criminals and people laundering money, of course, governments and people evading international sanctions, the Democratic People's Republic of Korea, most famously perhaps. People in countries where there are controls on the export of capital export controls, or where there's hyperinflation, or with high levels of corruption. And I'm just giving examples of countries that may have satisfied this criteria at some time in the past. But anyone who has a need for money, whether for legal or illegal purposes, and as with money itself, one type of users are the investors who think the value will rise, why people hold US dollars or they switch to Japanese yen at different times, because they think the value will rise and they'll be able to sell it at a profit. So that was Bitcoin. I'm going to talk now about distributed ledger technology. And there is a subtle difference between the word blockchain and the words distributed ledger. And I'll show that in a moment. But most people in this area, in this field, talk about them interchangeably. I think the difference is only important if you're talking about structures or architectures that are not themselves blockchains for one reason or another. And I give you another metaphor, and this is to distinguish blockchains from the World Wide Web. Some of you may have heard me tell this story before. The way I think about it is that what the World Wide Web did was make it easy to disseminate information, and in particular, one way to think about it is that we could imagine we have an infinitely tall skyscraper, a building with many, many floors, an infinite number of floors. And on each floor, there are rooms with whiteboards in them, classrooms, if you like, with whiteboards and tables and chairs inside the room. And with the World Wide Web, or with the internet, in fact, you can go into any room, you can check to see if it's empty. And if it's empty, you can go in and you can start writing on the whiteboard. And if it's an open web page that you've created, then anyone can wander into that room and sit down and look at what you've written, what you are writing while you're doing it, or what you've written on that whiteboard. And they can wander around. And if the content that you've written is only meant for certain people, it's restricted viewing that you want to give, then you can put a lock on the door, a passcode on the door, and you can give that passcode only to some people. So you can create an intranet, so a private network, just for a private internet, just for some users. That's the World Wide Web. Blockchain or distributed ledger technology is the same. It's another skyscraper, infinite number of floors. Each floor has rooms, but classrooms. But in each classroom, there's not one whiteboard at the front. There are at least two whiteboards. There's one at the front and one at the side. And the one at the front is the main board where you show stuff off. But the rule is that when you go into an empty room and you start writing, you have to first write on the sideboard. And that doesn't get displayed publicly. that's like a practice board or a rehearsal board. And the content that you put on that rehearsal board only goes onto the main board if the people in the room vote to put it on the main board. So you write what you like, but the people in the room vote on whether it should go up on the main board, or a majority of the people. And you can have any number of voting rules, different types of voting rules, but we could just say majority voting. That will cover this. And if they agree to put it up, then you can put it up on the main board. You can't take it down unless a majority allows you to take it down. So it's a lot, in a way, it's a lot less freedom for the writer. But what it means is that the people in the room have approved this information. And again, as with the web, you can put a lock on the door, and so only certain people can be allowed in the room. You can permit people in or not permit them in, and it's the ones in the room who have the voting rights for that particular distributed ledger. So what this allows, there's some witnessing going on of the data that goes up, and the witnesses, only the witnesses who happen to be in the room at the time are allowed to agree for data to come down. But this allows, what it allows us to do is to share data in a tamper-proof way, which is quite, as I said earlier, quite amazing that by having this being witnessed, you're making it tamper-proof. You can change it, you could try and rub it off, but everyone in the room will see you do it, and they know their voting rights, so they'll know that they will vote you, prevent you from doing that. In computer science parlance, we would say that the people in the room, the nodes on the network, have agreed a shared state for the variables that these values are being stored. The distributed ledger also preserves the history. So we chain the blocks together, we stack them on top of each other, if you like, and we have the history of the past transactions in the case of transaction. So the terminology we use in computer science is that the protocol is stateful. The hypertext transfer protocol, which I'm sure everyone listening to this has used sometime in their life, is stateless as it was invented. It doesn't keep track of history, which is why it's susceptible to distributed denial of service, DDoS attacks, because the attacker just repeats the same command and the server, or the same request to the server, and the server doesn't realize that it's seen this before and tries to respond to it. HTTP, the hypertext transfer protocol, has been modified to add history or to add ways of tracking history. So for example, through cookies, there is a way that tracks the way they track history, can track history, or through forcing people to register their email addresses and so on. But these are fixes on the basic protocol. So the basic protocol is not stateful. Distributed ledgers are stateful shared state. And that description or those features can prevent the double spending. The applications or the usefulness of distributed ledgers has evolved, particularly since about 2015. And I have seen this in my conversations with people in business. Up until about 2015, people thought this technology was only useful for cryptocurrency transactions. But people in banks realized that maybe it's useful for other currency transactions. So if I wanted to do foreign currency trades between, say, US dollars and euros, then I could keep track of that with distributed ledger. And one of the first projects I ever worked on in a commercial world in this space was for a bank that wanted to eliminate the use of SWIFT transactions, the International Financial Agreement, the agency that does international banking transactions. They wanted to eliminate the use of those transactions for internal transactions, so between one branch of the bank and another branch of the bank. And we built a prototype platform for them. There's a siren going past my place at the moment, you might have heard. Anyway, from currency transactions, people realize, well, maybe it's not only transactions of currency or cryptocurrency. We could think about exchanges of transactions of any assets if we have a digital representation of that. And not only exchanges of ownership, but exchanges of custody. So who owns an asset might be very different from who has possession of it at the moment. There are many works of art sitting in vaults that change their ownership all the time and never change their physical custody. They stay in the same vault. And then people started to think, well, records of information, particularly information that doesn't change very often. So personal identity, corporate identity, data provenance, if we're trying to track where data came from and keeping track of that data, just keeping the information around so that we can do searches of provenance on it. And then people began to think promises and commitments for things like futures contracts or insurance and more recently complex performance contracts. And I'll talk about an application of that. But insurance is an example where it's just a series of mutually reinforcing and interlocking promises. I promise to pay the insurance company a certain amount of currency money every month. And in return, if I do that, if I keep that promise, in return, the insurance company promises to pay me a large amount of money if there's a fire in my house, for example. So I'm promising to make regular small payments in return for the possibility of a single large payment or even multiple large payments, depending on the contract. And these are just promises. A big issue is if I or the insurance company go out of business during the period of the contract. And so we have regulation around this to deal with the situation. I've just made this table. I won't go through it all, but thinking about some of these benefits and what happens with them and some applications. So if you look at the first one, being able to store permanent records on a distributed ledger is of most use when we think about identity information, maybe also with promises. And so the applications are registers of assets, futures markets, and insurance, which are promises. I won't go through these, but this is just an example of the analysis that's possible of the different types of applications. And now we have scores, if not hundreds, of different application types. I'm just going to, while you read that, just as I mentioned a few moments ago, there's a difference between the idea of blockchains and distributed ledgers, and many of the architectures that have been proposed and even implemented do not involve transactions. Even if they do involve transactions, may not involve the transaction being put into blocks. And even if they are put into blocks, may not involve the blocks being chained together. So the ones which do involve those things, blockchains, are on the left of this, the first fork of this picture, reading from the top down. And we commonly talk about permissioned or permissionless. So permission systems are closed. Think about those as closed. Permissionless systems are the open ones, such as Bitcoin and Ethereum. Anyone can join, anyone can see what the transactions have been. There are other distributed ledgers. The architecture proposed by Corda, which was developed by a consortium of banks called R3 CEV, R3 CEV, doesn't necessarily chain transactions together. It doesn't put them into blocks, doesn't chain them together. Things are not witnessed generally by the entire community, but by specific nodes called notaries who have that role of witnessing and witnessed by the parties to a transaction only, so not by other people. This is just to give some structure to these different terms. I still use blockchains and distributed ledgers interchangeably, unless I'm talking about one of these specific. Now, why would we consider a distributed ledger? Why would we not just use a centralized database? I have had this argument at least 100 times with my fellow computer scientists, many of whom do not realize that there are other aspects to life besides information technology. There are other disciplines, there are other forces on people besides what works best in theoretical computer science. So many people argue that centralized databases are superior to distributed ledgers on technical grounds, sometimes on costs, on simplicity, on energy usage. And their arguments might, I'm willing to concede, their arguments might even be true. The fact that they are true or not is irrelevant to the decision being made by corporations when they're considering distributed ledgers or shared databases. The first fact that many commercial applications have to take into account is that most countries have antitrust laws. They have laws against restraints on competition, pro-competition or antitrust laws. And those laws make it difficult, if not impossible, for a company to have detailed data or to hold detailed data on their competitors. So I've seen many potential applications where a group of companies in one industry think there is value in sharing the data that they share between each other, which they might share with emails, they might share with common access to a central database. They think they could do this more readily with a distributed ledger. The laws against antitrust activity are so strong, however, that even to have a meeting about discussing the possibility of a distributed ledger may breach antitrust laws in some countries. And I've seen several projects where before there's even the first meeting about the project, the companies involved, who are all large companies, the companies involved seek some legal advice and say, can we have a meeting? Does the meeting itself breach, the calling of a meeting, breach antitrust laws? And in some jurisdictions, under some interpretations, it may well do. So the advice usually from lawyers is that the companies should first agree before having a meeting. They should first agree a statement about what the meeting is about, agree amongst themselves, and then read this statement out and even put it on the wall during the meeting. So the antitrust laws is a factor in this, a very strong and very important factor in the decisions about what type of architecture to use, which I say repeatedly to my computer science friends. So given those antitrust laws, the choices are not for a group of companies. Generally, it's not legally possible for a group of companies to build a centralized database and run it. They either have to use a distributed ledger or they have to find a trusted third party to build and run and hold the database for them. It can be a centralized database, just can't be held by the participants to what the project is. There are companies that will do this. There are companies that will offer this trusted third party service. The big four accounting firms, legal firms, specialist computer security firms. There's a score of companies at least who will offer this service for you. As far as I know, none of them will do it for free. So you have to pay them to offer this trusted third party service. And if you have to pay them, then companies say, well, why are we paying someone else when we could build it ourselves as a distributed ledger? Moreover, if in many applications, the data gets shared between the participants and the pooling of the data, the fact of bringing it together, creates a business opportunity. So pooled data has information that arises from the fact that you're looking across an entire industry or along an entire supply chain, whereas the data from each company is only partial. This is complete. And a common example is that if you've got that pooled data set, you can use it for predictive analytics. You can predict where there's likely to be supply chain blockages if you have data all along the supply chain from all the major participants in the supply chain. So there's commercial opportunities from that database or that distributed ledger. And again, if you give it to a third party, the third party is the one who's going to realize those, who's going to make the money. So many consortium partners, participants say, well, why shouldn't we make the money? We're going to build the distributed ledger. We'll make the money that comes from sharing this data. And distributed ledgers provide a platform of sharing the data in a tamper-proof way. And they basically provide a computational basis for the trust between the competitors. So you may have heard it. I just get sick of hearing this statement. I hear it from theoretical computer scientists and people in universities that the only people building distributed ledgers are technologically idiots, whereas in fact, the people building distributed ledgers in business are among the brightest people I know and are constrained by those regulatory constraints and by the commercial considerations that are factors in this decision. I've ranted, I've got that out of the way. Smart contracts. So I'm just giving, some of you will know this stuff, some of you will not. I'm just going to give you a brief introduction. So a smart contract is really just an automated process. The terminology dates from 1996, I think, before blockchain came along. But basically, we can think of it as a computational version of an agreement between two or more organizations. And a computational process, one way to think about them, common in computer science, is that we have inputs with some process that transforms those inputs, and we generate outputs. So an example, which I know of, is taking as inputs satellite images of wheat fields. You can acquire these images for free from NASA. The three biggest producers of winter wheat are USA, Canada, Ukraine, which is in the news at the moment. And you need weather forecasts, but with images of the field as it is right now and a weather forecast for that region into the future, you can predict the best date for harvest, and you can predict how much wheat just from the image and the weather forecast. You can predict the quantity and quality of wheat that will be produced from that harvest, which to me is just amazing, just from an image. And so there are companies that do that. They generate forecasts of the supply of wheat, best harvest dates and crop quality. The customers of those companies include the large farmers. So there's a bit of self-fulfilling prophecy in here. If I make a prediction of the best date for harvest and I sell that prediction to the farmer, he's likely to use it. So my forecast becomes somewhat self-fulfilling. It doesn't matter, it's still an accurate forecast. And with that forecast of the supply of wheat, I can combine it with a forecast of demand, and I can figure out what I should do with regard to wheat futures. So I should buy those futures for the dates around the harvest time, or not buy them, or what have you. So this is an example I know that's been automated with smart contracts, starting with some very heavy processing, cloud processing of satellite images. For non-computer scientists, computer scientists like to think in terms of hierarchies or layers sitting on top of each other. And this is just my picture of the hierarchy. So we've got the internet and the World Wide Web at the bottom, distributed ledgers with their two parts being the messages and transactions on one side, one layer, and the protocols that deal with those transactions above them, forming distributed ledgers. And then smart contracts are things that run on top of certain distributed ledgers. And the applications like that wheat futures forecast that I just mentioned sit on top of the smart contracts. So this is just a way of understanding these different. There are lots of applications. Again, I won't run through this because I'm going to talk in detail about. So this is just there to let you know that in those different types of application that I talked about, there are major companies. I would hazard to guess that of the Fortune 200 companies, at least 180 and maybe all 200 have had teams look at blockchain. I know of companies in the Fortune 200 that have 20 projects, 20 or 30 projects going on blockchain. Some of those fall by the wayside, they don't go to fruition. Some go all the way through, and some indeed have gone all the way through. This is not minority technology. This is something that has taken the large corporate world by storm, and why I think it's a revolutionary technology. So one application is in trade finance. We have some widgets built in a factory, say in China. They move, when they leave the factory, they travel by road to a port. They go through customs, Chinese customs. They travel over the sea, the horizontal part of this picture, they travel over the sea. And they arrive, say, in Britain, and they go through British customs and then travel over the roads, and they end up in a supermarket. So reading this diagram from top left, across, and then going up to the right. At each point, the goods, the widgets are in a different physical location. They have different custodians, people looking after them. They might have different owners. They will have different owners, but where the ownership hands over might be different. Many products are owned by the factory all the way until just before they reach the supermarket. Some products are taken by other middlemen, by intermediaries, middle people, I should say, at different points along the way. Whether or not, so one aspect is ownership, a second aspect is custody, a third aspect is finance, and trade finances give loans, bridging loans to various parties in the system. A fourth aspect is insurance, and the insurance might be only for the part while the widgets are on the ship, while they're on the high seas, and then only if the ship agrees to an approved course, for example. So insurance can come and go, finance can come and go. Keeping track of all this, it's helpful. These different organizations are using the same data, and keeping track of it it's very helpful if that same data is in one place, if they're able to share that. So the various trade finance projects, some of which are in production, they're being used. This is an example of these. Vact is an example I know quite well, which was launched in November 2017. And this project is a blockchain project for all the logistics activities that happen immediately after futures trade contract is signed. So we have an energy futures. Shell might decide to sell some oil to BP for delivery in 3 months' time, and they agree that over the phone or via email, and they sign a contract, they exchange the contract by PDF. And then there's a whole bundle of activities. They've estimated something like 200 separate activities have to happen until all the delivery has been made. And there's 40 or more different organizations. The oil companies, the companies that check the quality, the companies that deliver it, the shipping company, the ports, the banks, the insurance companies, all the participants in this complex chain. The big problem they had before Vact was data reconciliation. And that's when two companies are looking what they think of as the same variable, but it has different values. So one says, Shell thinks the delivery is for the 1st of June, 2022, and BP thinks the delivery is the 10th of June. So they have different dates, and their own records might not, it may take some time to find who was wrong in this. Their records might not, it may be just something that was agreed between them that somehow got written down or misunderstood. And so there's a lot of effort, before blockchain, there was a lot of effort in investigating and digging into and finding the sources of these irreconcilable data items. That was a heavy task. What distributed ledgers do is automate that task. So we've found a way to automate the process of data reconciliation. In fact, the only way, it's the only way to automate it. More recently, I've seen a case, and this is between an oil company, Equinor, and a blockchain as a service company called Datacumba, where they are trying to automate the production and the checking of invoices. So in a contract between an oil company and its driller, there might be 150 or more billing triggers. So how much they get paid depends on how long they drilled for, in what direction, whether it was vertical and horizontal versus whether it was at an angle, in what sort of rock, under what weather conditions, whether it was at land or at sea, and so on and so on. And these conditions might change at short notice, or they might change over short time durations. So creating the invoice by the driller can take the driller months of effort. It can take the oil company months of effort to check that. And it turns out there's lots of opportunity for fraud and collusion in that process between individual people in the process. Alternatively, we can have Internet of Things devices to collect the data at source, to automatically upload it to a shared platform, blockchain platform, to process that data to create the invoices and to check that data once received as an invoice. So the whole process can take from 9 months to a few minutes, depending on what actual parts of the contract are automated. And it eliminates lots of opportunities for fraud and collusion. I'm not sure how long I have, so I think do I have another 10 minutes, Alex? Okay. I'm hoping that was yes, I didn't hear you. But,
I forgot to unmute myself. Sorry about this. On my side, yes, I would say so. Please go ahead. It's fascinating.
Okay.
So 10 minutes should be fine okay. On our side.
Okay. Oh, then I can take a bit longer then. Okay. So I'm going to talk about the current landscape, and this is a graph that many of you will have seen, the Gartner technology hype cycle, and they argue that many new technologies undergo increasing hype as they become more well-known. They reach what Gartner called a peak of inflated expectations. Then people are disappointed with them. There's a trough of disappointment. They don't turn out to do all the things that they were promised. They don't solve world hunger, after all. And so there's sort of disillusion with them. But most new technologies are still useful for some tasks, and over time it becomes clearer what those tasks are. And so we get what's called what Gartner called a slope of productivity, slope of enlightenment, sorry, and a plateau of productivity. So I'm not sure where I would place blockchain and distributed ledgers on this graph. I've on record as saying that there's an enormous amount of hype. There has been, and there still is, an enormous amount of hype about blockchain and distributed ledgers. And I'm on record of saying I think about 90% of that hype is entirely justified. I think the hype, I believe the hype, and it is entirely justified. I've seen the benefits that have arisen in commercial applications. Almost all of the commercial applications I've seen are permissioned private systems that are not public and are not, people don't talk about them, people don't know about them. But in general, for people who in the outside world who are not involved in those systems, then probably we are past the peak of inflated expectations. They probably think we're down in the trough. But I don't think there is a trough. I think this is revolutionary technology, and the revolution is still happening. Where are we in terms of typical development of systems? So from 2015 onwards, companies started to explore these. Typically, for any application, they would build some proof of concept, POC. And then if they proceeded, they didn't all proceed, of course. That's the point of a proof of concept, is to see whether it's worth proceeding. And if they proceeded, then there would be some small-scale deployment generally, and then large-scale deployment. And we are seeing, so small-scale deployment is what IT people talk about as being in production. So systems have started going into production from maybe 2016, and now they're starting to build up in scale. One of the constraints on building up in scale, as I'll say in a moment, is the constraint on scalability of the technology itself, quite apart from scalability of a particular application. The technology itself has problems regarding scale. What are the challenges? So there's some technical, I call them technical research challenges. You need some research. Where this research is happening, some of it's in university, but I think more common it's not in university. As an aside, let me say that computer science is an exception to the general rule of pure research coming before application. In computer science, in its history, most applications have come first and theory has come later. So we've had programmable machines. They were textile looms invented by French weavers in the 1720s. We've had programmable machines since the 1720s. Britons think that this happened in the early 1800s with a jacquard loom, but in fact the French beat us. The French beat the British. We didn't have a theory of programming worth its name until the 1960s. So we had programmable devices working in industry for 250 years before computer scientists had a theory of what was going on. Babbage his machines didn't work, but other people's machines at the same time worked at that time. Babbage was a century before Turing. So this is a commonplace thing. Bitcoin, blockchain happened before we had a theory. And we're still developing, as I say here, the conceptual framework. We're still coming up with this conceptual framework, and we don't have that yet. There are lots of technical problems because this technical domain is still quite immature, and most importantly for IT technologies, the tools are immature. The software development tools are still immature. The languages are not very sophisticated, the programming languages, and the tools for developers are only just starting to appear. We have problems of scale, we have problems of speed. We don't know yet what designs are appropriate for what applications specifically. We have a problem of verification, how we verify smart contracts as an example. We don't have a good theory of robustness against attack. There's still possibilities of attack. And we have technical issues about privacy on networks, particularly on open networks, but even on permission networks. I have a picture of a medieval farmer with a plow, because that's how I feel the technology is. We are in the very earliest period of this technology. For comparison, I'd just like to point you to the World Wide Web, which came about at the end of 1991. And at the very beginning, 1992, 1993, it would have been possible to have blogs. But people didn't set about creating the software tools to make blogs until a decade later. So we could have had blogs commonly used in 1993. They didn't come along until the 2000s because the technology was capable of it. It's just no one had got around to doing it. And that's exactly the same with many of these challenges. There are challenges with implementation that, as far as I can tell, are not the subject of academic research pretty much. I don't know much on this. So one of these is data management, dealing with privacy, confidentiality, storage, replication, ownership, exploitation, IP issues to do with the data that's held in systems. There are enormous challenges to do with production readiness and integration with legacy systems. Canadian technologist named William Mugia says that it takes 18 to 24 months to finalize an application after a proof of concept, after a successful proof of concept. And that's basically all the things you have to do to get your proof of concept to fit in with the rest of the legacy systems in a corporation. Most large enterprises, most global ones, have grown by acquisition. They've bought other companies, and when they buy them, along comes with the purchase the IT systems of the companies that are acquired. And so most big corporates have multiple IT systems conflicting, having to work together. And the challenge or the cost of replacing them with one single IT system are generally too large. Those projects would be too large or too expensive to contemplate. So they live with their legacy systems, and that creates problems for any new technology such as this. There's a challenge in implementation with regard to the management of access rights to the data. And this is an area where there might be scope for computer science research, and I'll mention it again in a moment. As far as I know, there isn't yet an access rights framework that covers what we want in commercial blockchain applications. What we want, what we would require, in fact, are assignment of access rights, which are automatable, dynamic, decentralized, delegatable, specific to particular items, limited by time, constrained by events, limited by task, and revocable. And if I just take one of those words, decentralized, I think all the research in computer science on frameworks for access has been on centralized systems, where there's a central administrator, a trusted party. Here we don't have that. So what can we do? Is there a framework we can use that's decentralized? But all of these are relevant. We mostly don't have user-friendly interfaces and APIs. That was not part of the design of Satoshi Nakamoto. It was meant to be an open system, and if people wanted to put their own interfaces on this, then they're free to do so. And they do, but many of these are not user-friendly. And with large corporates engaged in multiple projects, then there are issues to do with managing multiple distributed ledger platforms. They might be built on different technologies, they're built with different partners. How do you reconcile data between them? Sharing data between blockchains is still an open issue. And they will, for each, even permission systems will still use the public-private key infrastructure. And each of those systems, a company might be in that system or on that system in multiple roles. Talk about Vact and the oil companies, that might be, they might be a seller of oil, they might be a buyer of oil, they might be a shipper of oil, they might be a broker of oil, they might be a quality tester, they might have an arm that tests quality of other people's oil, in multiple different roles. And each of those roles will have at least one public-private key pair. So how does Shell, how does a company manage all those private key pairs? Where do they store them? Who do they have look after them? How do they manage the authorization of them? These are things for which, as far as I know, there are no general answers. There are people are finding answers themselves in each case. Products are coming out, but the products don't meet everyone's needs. That's still very early days for systems or software that help people deal with these. As well as those technical and implementation challenges, there are organizational and legal challenges. These are because these systems are intended and used by consortia, by groups of companies, and how you manage the stakeholders, how you manage joining and revocation of membership, so on. There's generally a business process engineering, re-engineering task, particularly when different companies are sharing data which gets used in common processes across them. There's management and governance, for example, of the keys, as I just mentioned. There's the issues of data ownership, privacy, and usage. And then you get legal and regulatory aspects like the competition and antitrust law considerations I mentioned, questions of ownership of IP, data privacy and management, and most famously, the legal status of smart contracts. We don't have good legal understanding of the status of smart contracts, except possibly in Malta, who has passed some laws about this. But I think everywhere else in the world, it's still being discussed. One of the legal societies, the SRA, solicitors, I'm not sure who it was, maybe it's the Law Society, just recently released a white paper looking at this issue. Only recently released this. There are academic research challenges, and I mentioned the ones here that I think are the most important. So one of these is a challenge about community governance of these systems, particularly for open systems, but even for the permission systems. What's best practice for community governance? What is even good practice? We don't know. We're still in the early days. And this would be the people who might be able to bear on this, people from within computer science in the computational social choice domain, or people in political philosophy. If we have, we have theories, I've read books on theories of democracy, we have theories of how to organize the political regulation of societies of humans when, or on the assumption that the people in that society are relatively stable. So we have different theories of how democracy works. I've read a lot about that, about societies, but the assumption is that it's one community or one society, one group of people. In these open blockchain systems, it's not a single society or one group of people. It's an ad hoc system. People coming in and leaving. The people who found the system might disappear, they might go away, they might leave, they might go and they might fork off and find their own, another fork of the platform. So what's a theory of democracy that works for an ad hoc community? I don't think that exists. I'd be delighted to be wrong about that. But political philosophy, I think, could contribute a great deal to this. What are the specific rules? How do you punish people who can just leave? You can expel them, I suppose, but they could rejoin under a different pseudonym. So there are lots of issues there. There's a whole set of issues which some of my colleagues in King's are working on. Carmine Ventra, I don't know if he's on the call, but the crypto economics of open platforms, how to mix the incentives and the disincentives in just the right way to achieve desirably global behaviors that are global behaviors that are desirable for the good working of the system. They may not be desirable for individuals, but they are desirable for the system as a whole. There's less need of these in permission systems because you only let in people who form the platform, only allow in others who they know and trust, but it still may have a role. There's still a possible role here. The question of verification of smart contracts, which I've worked on a bit myself. The biggest idea here is from Christopher Clark at UCL, and that's the idea of computable contracts, which are contracts which are both machine readable and human readable, as a way of bridging the gap between natural language contracts and smart contracts. Another approach is to say, well, the people who know best whether a particular smart contract will be successful or not, excuse me, the people who are best at assessing smart contract code are other developers of smart contracts. And so this organization, Nexus Mutual, has been created to allow for insurance of smart contract code by saying, someone says, I would like to insure this code, and they make their code available to others to check. And if the others think that it's got no bugs, then they can pledge to insure it. If they think it has bugs, they will not insure it. So this is feedback to the coder, feedback to the developer about whether the code is going to do what it's supposed to do. And then the last one is this access right frameworks, the frameworks for access rights for these systems, which I just repeat there, the requirements that I had before. I summarized, I've said this is a revolution, and I think it's the second revolutionary IT technology that has happened in my lifetime. First was the World Wide Web, and distributed ledgers, I think, as the second. So what the web enabled was, reading across this table, the web enabled easy dissemination of information. The era has come to be called information society, and what computer scientists would call native applications, that is the ones that are inherent in the technology, database access, advertising, e-commerce. A benefit of Amazon, which is not often recognized, is that Amazon provides free access to the world's largest book catalog. So if I can't remember the author of a particular book, I can go on Amazon and I can search the title, find the author. Or if I want a set of books on a particular topic, I can search Amazon. I don't have to buy a book. I don't have to even register with Amazon to do that. I can get that information. Amazon is giving me access to a database that they have created. And it's been remarked that this is novel. This hasn't happened before in human history, that all of us, anyone with access to a computer, can now access the world's biggest database, the world's biggest catalog of books. The impact of the web in the 1990s was there was a wave, a decade of business process engineering and business process re-engineering inside organizations. In around 1994, I remember seeing adverts in the Wall Street Journal put there by IBM. They were full-page advertisements. They had a IBM logo, and all the advert said, most of the page was white. All that was written was the following words: "We will get you online, full stop, 3 months, $1 million." So IBM was promising to get a company to have an online presence in 3 months and for $1 million. They could have got online in half an hour, but they didn't have the skills to do that. But what IBM was really doing was promising to engineer the back-end processes, the processes behind the online presence. So a company might have an online presence where they sell a version of their products to customers, but they need to have the back-end to fulfill those sales. So that was why there was 3 months and why it cost $1 million. But that was an example of the need, and IBM was not at all embarrassed about charging $1 million for 3 months' work. Of course, it would be a big team. I think there'll be a similar wave, there is already started, a similar wave of business process engineering and re-engineering across organizations this time, and that's from blockchains. So the second row of this table, blockchains and distributed ledgers, the interest started around 2015. And what it enables is sharing of data in a tamper-proof way. The web enabled us to share data easily. Blockchains enable us to share data in a way that is tamper-proof. So we know that it hasn't been altered by someone in the middle. We know that it hasn't been altered by the recipient. The recipient can't claim not to have received it if they're a participant in a blockchain where that data is available to everybody. So they can't claim they didn't see it, or they didn't know it was that, or they thought it was something else. And so we get agreement on shared information and shared actions. I don't think the terminology information society captures what's going to happen and what is happening with this. I can't find a good term, but the best I've come up with is joint action society. I think we're in a phase where we're building on the shared information to take joint actions, common business processes between business partners. And there are lots of native applications, which I've mentioned through the talk, where we are exchanging, where a good is being exchanged or the custody is being changed, the change of custody. Complex workflows like the Equinor and Data Gumbo oil drilling case. Insurance is one of the main ones. So these are just, this is just my summary of what I think is happening, why I think this is a revolutionary moment. There are other aspects to this space, which I didn't talk about today, but I just mentioned because I know many people are interested. All about adoption and development of cryptocurrencies, including the trend towards central bank digital currencies, initial coin offerings, which have proven themselves to be a very successful way to raise money when all you have is an idea. That's all you have. Non-fungible tokens, whose goal is to bring online the scarcity that exists in the physical world into the online world. And the metaverse, if the metaverse is to come into being and is to be successful, we will need data items to persist through different domains. So if we have some cryptocurrency that we're using in Amazon's metaverse, we might need to use the same currency in Microsoft's metaverse. How do we get that persistence? That can only be done, I think, with access to tamper-proof multiple stakeholder data storage, and that means blockchains and distributed ledgers. So there are many different views on these different other aspects. I haven't got time to go into all of them. I will express my opinion on most of them through a picture, which will be my last slide, and I'll thank you for listening. Those who know their flowers, that's a picture of some tulips.
Peter, thank you very much. And a round of applause, virtual this time, from all of us. Thank you. It was fascinating. I know that we are a little bit over time, but I think we still have the possibility of space for maybe 2 or 3 questions. Please do raise your hand in case you would like to ask questions. Those of us who are still in the room. Well, I do not see anything here, Peter, but let me ask you just one question now in closing this extraordinarily interesting talk. Where you mentioned at the start the multiplicity of protocols, you mentioned at the start that we have proof of stake and proof of work. Recently, when I was on FieldWork a couple of months ago, I talked to a software engineer working on a blockchain protocol, proof of memory. And a lot of them, where do you see them going, these protocols? We would expect some to survive, we would expect all of them to survive, we would expect only one to survive. Where do you see that evolving?
So I think they all have positives and negatives, advantages and disadvantages. And that means each one will be better suited for particular applications than for other applications. So I would say they will probably all survive in one form or another for particular applications. And new ones will continue to be invented. One of the nice features of the architecture of blockchains is that you can plug and play. You can take the code that's open source code for Bitcoin blockchain, and then instead of using proof of work, you can have some other protocol. And that's a common approach. For permission systems, I would say the most common platform is Ethereum, but not the public Ethereum platform, a private version of Ethereum. So you take the Ethereum open source software and you make a system inside the closed room. And there they typically use proof of authority. So if you are a node in the system, you have the right to, or that you maybe have the obligation to upload transactions and blocks every so often. So I think all of them will survive. Alex, it's a good question. I think all of them will survive in one form or another.
Thank you. So I have a question here from Misha Dollar. Yes. So I see this hand raised. Misha?
Hi, Misha. You're on mute, Misha.
1 second. Okay, can you hear me now?
Yeah.
Okay, great to see you, Peter. So I have a question. Blockchains clearly rely a lot on cryptographic methodologies, algorithms, and protocols. And at the same time, we have now quantum emerging. It's really gaining momentum. And there are claims that in a few years' time, we're able to break some of these cryptographic protocols. So where do you see this going? Do we need entirely new cryptographic methods which are quantum resistant, so to re-engineer the blockchains for the future? Or, I mean, what is your feel in that?
So thanks, Misha. It's good to talk to you, and it's a very good question. I'm not a cryptographic expert, so I wouldn't like to make a prediction of when it will be possible to use quantum computers to hack the private keys, to find the private keys of people. But everyone expects there will be a day or a period when it can happen. People I've spoken to think that it's 20 years away. Some people think it's 100 years away.
Okay.
But there's definitely a day, and it might be easily within our lifetimes.
Okay.
Already, I've seen papers. Already, there are people working on how you transition. What should you do as a node on Bitcoin to protect your Bitcoin private key, or what should Bitcoin do to protect it against quantum attack. And there are proposals that could be implemented. Who knows whether that work or not, but there are proposals that would transition from the particular keys we use now to longer keys to make them more resistant to quantum attack.
That's interesting. But once you know, would we be able to protect also the Genesis block, or can we expect then a lot of Satoshi Nakamoto's come out suddenly in 2030 and claim I was the one who owned the first block? You know.
So part of this would be something that the community of Bitcoin nodes would have to agree. But part of it might be to say we basically fork the blockchain onto another system where every amount of currency is locked, can't be transferred unless you are able to present the private key. You need some way to have some other evidence that the person got their key somehow without hacking it like that. I don't know how that would work, but that might be way. Or you might just say we give up. We just if the hackers want to get Satoshi's currency, that's fine because we're all going to be on another blockchain where we're doing it instead of Bitcoin. But it's a hard problem. It's definitely a hard problem.
Okay, thank you. Thanks, William.
Thank you.
Sorry, Misha, if you do hack it, I want half of the amount.
I was about to say, you know, I wasn't sure whether now to continue my investment into quantum or not. By the way, Peter, now on a more serious note, you know, I mean, sitting here in Silicon Valley, of course, everybody talks about the metaverse. And you mentioned, you know, the necessity of actually using ledgers in one way or another. So it would be interesting maybe to sync offline and anybody else on the call who's interested in that to see where there are synergies.
Sure, yes, certainly, Misha.
Perfect. All right, thank you.
Yep.
Thanks,
Thank you. So, Peter, one last question before closing the session. You painted a picture of blockchain and distributed ledger seeping into various domains, into various industries, different applications, and so on and so forth. And on the other hand, we've heard time and time again this line of criticism. It consumes a lot of energy, way too much energy. You know, it has a negative impact in relationship to these efforts we are making towards reducing or mitigating climate change and so on and so forth. What do you have to answer? What are your thoughts on this issue?
So, thanks, Alex. That's a good question, and I've been asked it before many times. The applications I'm talking about in the commercial world are almost all, they're not entirely all, but almost all closed systems. So, or what we call permission systems. And in permission systems, you can only join if you're invited. Normally invitations are to corporations, to enterprises. And normally the enterprises have to sign a contract, an agreement. So firstly, participation is not anonymous. The participants all know who the others are. And secondly, they will have signed an agreement in which they typically say these are the bad behaviors we will not do. And if we do any of these bad behaviors, we will suffer some punishment. And the punishment might be fines. It might be even expulsion from the system. So there's strong disincentive to do the bad behaviors. And why would they? Like they're in it for they're participating for some commercial reason. So they want the system to work for commercial reasons. So those factors mean that you don't need to do the proof of work protocol. Mm-hmm. So you also don't need to you don't need to reward the participants who do the mining. You don't need to reward them with currency. So usually you don't in fact need any currency. The reward they get is because they've got some commercial business reason to be in there and they're promoting their business reason. And you don't need to disincentivize them by making them do some proof of work. So the most common protocol in those permission systems is it's a version or a type called proof of authority. And that just means they take it in turns. It might be, sometimes I've seen it as one company says, we'll do it all the time, or they each take a week, they do it for a week. The the Facebook project for a currency called, most recently called Libra.
Libra.
Yeah, previously they called it Diem, which they sold a week or so ago. They sold this project. But in that project, the idea was that they had 100, they were aiming for 100 partners. And each of those partners, I don't know how many of them, of the 100 they got, they signed up, but they signed up, I don't know, maybe 50. Each of those partners had the task of doing the processing and validating and uploading for a period, and the period typically might be a day, 24-hour period, or a period was variable in their designs as far as I know. What I saw in the documents was that they were thinking about it as being a day. They called it an era, but they didn't specify the length of the era. So then it would just be a turn-taking protocol. And the authority comes from the fact that you're in this select group. So that was an unusual one in that it was permissioned to be a node that would have this uploading power. You had to get permission, you had to pay $20 million as well. But the platform was supposed to be readable. Everyone could see all the transactions. So you didn't know who those transactions were of. Again, it was pseudonymous, but you could see the transactions. So the concern you've raised about the environmental impacts, part of me, I've done enough. Sorry, let me first say that that's only for the platforms that use proof of work, and the most famous one of those is Bitcoin blockchain. Mm-hmm. Ethereum uses proof of work, but is in the process of transitioning to proof of stake. It was always their plan, and they have started now to transition to proof of stake. So over time, in a few years, it will only be, the only main one will be Bitcoin blockchain. I've studied enough economics not to be worried about it, because if somebody is willing to pay for that energy, then it must have some value to the economy. And we should perhaps be worried about the source of the energy, the electricity that's used by mining. But if the source is green, if it's sustainable, then what's the problem? So maybe I think the attention on the platform and the protocol is directed at the wrong place. The source of our problem should be with the sources of energy of the miners. Anyway, those are taking me away from computer science.
Now I ask this because here this energy consumption aspect is raised so often against blockchain and against DLT. It has become partly, I don't want to say a cliche, but we hear it very, very often. So I wanted to raise this issue. Yeah. Thank you very much, Peter. It's been a great session. Thank you. Thank you all participants. We reconvene on the 16th of March with a talk by Vili Ledonvirta, a sociologist from the University of Oxford, on the topic of cryptocracy, the quest to replace politics with technology. So it's a very good connection in your closing argument, into your closing arguments, Peter.
Thank you, Alex, and thank you everyone for listening.
Thank you.
Please email me if you have questions.
Thank you.
Thanks. Bye.
Thanks a lot, Peter.